Right. So the next topic we need to discuss is this idea of continuity. And you probably have a very, I guess, intuitive idea of what continuity is. So a function is continuous if you can draw it without lifting up your pencil. I mean, that's kind of an intuitive idea about continuity. But it doesn't make a very mathematical definition. So a function is continuous at a point at a number a if the limit of the function equals the value of the function. So in other words, think about like piecewise functions. So you could have a piecewise function that, say, it is defined this way to, let's say that's x equals 1. And then after that, it's defined some other way. Like we'll just make it a constant there. So this would not be continuous at 1 because there is a jump. So obviously you cannot draw that without lifting up your pencil. But it is continuous at, say, let's say that's -2, because the limit going to -2 is coming to the same point from both directions, and the value of the function is right there with that limit. So that's kind of the idea. So let's go back to this one. We looked at this one at the very beginning of this section. So state the domain. We already have stated the domain is as x not equal to ±1, or if we state an interval notation, -infinity to -1, union -1 to 1, union 1 to infinity. And again, you just get that by setting the denominator equal to 0 and solving for x. So now the limit as x approaches 4, you can see that 4 is in the domain. So if it's in the domain, we really just have to plug it in. So we're just going to find f of 4. So 4 minus 1 over 4 squared minus 1, and that would give us 3 over 15 or 1 over 5. And so that one's pretty straightforward. Again, if a number is in the domain and it's not close to a number that's not in the domain, even though that's probably not an issue anyway, you really just need to plug in the number to the function. So as long as you have continuity, as long as you have this number in the domain, you can just plug it in and see what the value is. Now, there may be exceptions to that, but we'll get to those later, maybe. So what about when x is 1? So 1 is not in the domain. So you cannot plug that in because that would just give you 0 over 0, which is, you cannot evaluate that. So what do we do instead? So one method you can use is to simplify that. And hopefully you recognize you can factor this. So we're going to factor that as x plus 1, x minus 1. Then the x minus 1's cancel. And so this reduces down to 1 over x plus 1. Now you can plug this in because this one is continuous at that point. Now these are equivalent functions with the exception of 1. With the exception of the value x equals 1. Because it's not in this domain, but it is in this domain. So the limit as x approaches 1 of x minus 1 over x squared minus 1 is the same as the limit as x approaches 1 of this function 1 over x plus 1. And now this one's continuous, so we just plug that in and we get 1/2. And if I remember right, I think that's what we said in the first example in the last video. Is it continuous at 1? It is not continuous at 1 because the value f of 1 does not exist. And so it's impossible using the definition of continuity. This would have to equal f of 1, but f of 1 is not defined, so it's not continuous at f of 1. Which you can tell that by looking at the graph. But what does go on there, if we look at the graph, there would actually be a hole. So you might think some functions you may have seen like 1 over x. actually 1 over x. So, well, we'll say negative 1 over x. That'd be negative 1 over x. You can see it, these go in opposite directions, this going towards 0. So that goes up to infinity, that one goes down to negative infinity. But this one, we have 1/2 there, and yeah, I don't know what I won't pretend to know what it's doing, but it will go, and then you'll have a hole right there at 1, and then it will go do whatever else it's doing. That's probably not what the graph looks like, but right there, that is what it looks like. You do have this continuity, except you have a hole right there. So it's actually not continuous, but we just call that a hole in the graph, or a removable discontinuity. But the idea with the limit, which is really all you need for this problem, the idea with the limit is if you cannot plug in the number, which you should always just try plugging in the number. But if you plug in the number and you can't evaluate it that way, then there's some way that you need to simplify the function or change the function in some way. And there are a couple of different techniques for doing this, or a couple of different methods that we will use. So let's go back to this one. So the limit as r approaches 0, I think this one came out to 6 when we looked at the tables in the last video. So obviously we plug in 0, that doesn't work. And in fact, we end up with 0 over 0 again. So let's see if we can simplify this. And so let's FOIL out the top and see what happens. So 3 plus r squared, we get 9 plus 6r plus r squared minus 9, and that is over r. 9s cancel out. And let's go ahead and factor out. So we have 6r plus r squared. Let's factor out the r, and we have 6 plus r over r. Of course, these r's will cancel. 9s canceled out. And so now we have the limit as r approaches 0 of 6 plus r. And of course, 0 would be in the domain of that function. So we can just plug it in. So 6 plus 0 equals 6. And that's what we expected from the table that we did before. All right, so that's one method for evaluating limits, besides plugging it in and just getting the answer if it's a continuous function. The other way is to simplify the function. So sometimes you can simplify it, you can get rid of the problem. In this case, the problem being r in the denominator. Another method, if you have a square root, so let's see what happens here. So we have the limit as t approaches 0, square root t squared plus 9 minus 3 over t squared. And so if we plug in 0, we have square root of 9 minus 3, that gives us 0, and then of course 0 on the bottom. So this does not work. So what we can do here is rationalize the numerator. And I'm sure in algebra classes you have rationalized the denominator. This is the same thing, except we're going to rationalize the numerator, but it's the same idea. And so what you do is you write this term, but you change that to a plus. And so now we have a difference of squares, if you will. It's kind of a difference of squares. And so when you have a difference of squares, you're going to multiply this. This is basically a plus b times a minus b, and we get a squared minus b squared. So we really square that term, we get t squared plus 9, square the second term, which is 3, and we get, sorry, let me fix that. So t squared plus 9, we're going to square that term, we're going to square that term, and there's a minus in the middle. So there's our first term, there's our second term, and then on the bottom, no need to do anything with this. So just don't worry about multiplying this out. We just have this. And so now we have t squared over all that on the bottom. And what do we see? We see that the t squareds will cancel out. And that gets rid of the problem was the t squared on the bottom. So now we got rid of that. And so we have 1 over square root t squared plus 9 plus 3. And now we can plug it in. So these functions are equivalent. They just have a different domain set. But now we can plug that in. So t approaches 0, 1 over square root t squared plus 9 plus 3. And so plug in 0 for t, we get 1 over square root 9 plus 3, so that'd be 1/6. Okay, so if you have a square root, this is probably the way to go to evaluate the limit. I mean, you can try plugging it in. If that works, that's great. But if it doesn't work, just plugging in the number, then you gotta probably have to rationalize probably the numerator, but it could be the denominator. Either way, wherever the square root is, that's the part you're going to rationalize with this method. And then you simplify it, and you should be able to plug in the number at that point. So